fluid mechanics. So as I was telling you earlier, that the first section of this chapter is called hydrostatics, and it deals with fluids at rest. But then we have to specify what types of fluids exactly we're talking about. So we're talking about ideal fluids. So ideal fluids are defined as fluids, or you can say they're liquids, that have two important properties. So these important properties are, firstly, that they are incompressible. Okay, that means that they do not get compressed under excess pressure, and also that they are non-viscous. So I'll explain each of these terms. So incompressibility means that the density is uniform, okay, and unaffected by pressure. Okay. Unaffected by any changes in pressure. So what you realize is that no real fluid can be truly incompressible, because obviously under extreme amount of pressure, there will be some change in density. However, what we can do is real fluids like water, kerosene oil, etc., unless they are subjected to extremely high amount of pressure, that is, the amount of pressure is, the change in pressure is in the same kind of range as the atmospheric pressure, the changes in density are very negligible. So we can treat them as nearly incompressible. Okay. So additionally, we have to understand this point that real fluids are never perfectly incompressible, but many of them, like water and kerosene oil, are nearly incompressible. That means their density hardly changes unless subjected to extreme excess pressure. So within a certain experimental, you can say, bandwidth or pressure variation, we can approximate them as ideal fluids because they're incompressible. Okay. And the second property of being non-viscous, these are fluids which have negligible viscosity. Viscosity is the equivalent of friction. Viscosity creates non-conservative drag forces, similar to kinetic friction, okay, that oppose relative motion in a fluid. Like kinetic friction opposes relative motion. Similarly, and kinetic friction also, is a good example of a non-conservative force. So I think so far in whatever physics we have learned, kinetic friction is the only real world application example of a non-conservative force. So now, as we study more about fluids in this section, we will add to that the type of force called viscous force or viscosity. That will be in, of course, the second part of this section that we are studying, not in this part, not in hydrostatics. Okay. Because here we are dealing with ideal fluids, so the viscosity is absent or it's negligible. Okay. But when we come to viscosity, we'll see that they are another real life example of non-conservative forces which dissipate mechanical energy. And like kinetic friction, they also in such a way that they oppose relative motion. They tend to reduce the relative motion between two fluids or two sections of a fluid or an object moving inside a fluid, whatever we consider, okay, they tend to oppose the relative motion. So air resistance or drag force in air is also an example of viscosity. But there we are talking about viscosity of gaseous medium, which is also part of fluids in general. Or if an object is falling through water or any liquid, then it will experience the type of drag forces which are called viscous forces. Okay, so again, no real fluid is perfectly non-viscous. Okay, just like no real surface is perfectly smooth or frictionless. But under certain circumstances, we can treat uh, many real fluids like water, etc., to be almost non-viscous or have negligible viscosity. So in this chapter, it's a precondition that whatever fluid that we are dealing with, it has to be ideal in nature. That means it has these two properties, that it's incompressible and it is non-viscous. So in the absence of these two properties, some of the mathematical relations and all we'll develop will not hold true. Okay, they hold true only when we are dealing with ideal
water.
fluids. Yeah, I mean, water is an example of a nearly ideal fluid.
Sir, it's like a black body.
Yeah, but then black body is
In
something,
India.
which is, more elusive, because it's like, yeah, but in a sense you can say that.
Okay.
Or like even in the case of thermodynamics, like no gas is truly ideal. PV equal to nRT, it's only true up to a certain range and with a certain amount of error allowed. Okay, otherwise you have equations like Van der Waals equation, etc., which are better description of real gases. So something like that. Okay. But the idea is that, ultimately, again, physics deals with actual physical quantities, and the results that we develop in theoretical physics should agree with experimentation. So if we make certain assumptions like the fluid is ideal and the results that they are giving us theoretically, they agree to a certain allowed percentage error. Let's say that allowed percentage error is 2% or 1%. So the error is less than that allowed percentage error. Then it's as good as saying that, the fluid is perfectly ideal. That makes no difference at all. So that is the success of these theories.
So one
Okay,
second.
so yeah.
Okay.
Done, sir.
Okay. So now just some notation we will develop. Okay, density of an ideal fluid will be uniform, okay, at every point within it, and also independent of pressure. So we denote density with the symbol rho over here. As you know, it's a scalar quantity. It is equal to mass per unit volume. Okay. So it is expressed in SI unit of grams per meter cube, CGS unit of gram per centimeter cube, and you should know the conversion that 1 gram per cc is equivalent to 10 raised power 3 or 1000 kg per meter cube. So it's very simple. 1 gram per cc is 10 raised power minus 3 kg per 10 raised power minus 6 meter cube. So that's how it becomes 10 raised power 3 kg per meter cube. Okay. And you should also know that we define something called specific gravity, or it is sometimes also called relative density. For any material, and that relative density or specific gravity is defined as the ratio of density with respect to density of water at 4 degrees C. So this is a dimensionless quantity, specific gravity or relative density. And also something worth keeping in mind, density of water is 1 gram per cc or 1000 kg per meter cube. Okay. Density of ice for that matter is 0.9 gram per cc or 900 kg per meter cube. So you have that phenomena of anomalous expansion of water, that as water cools down from 4 degrees C to 0 degrees C and freezes, there is an anomalous expansion as water solidifies because of the unique hydrogen bonding that occurs in H2O molecules. Another example is density of mercury is 13.6 gram per cc. This is quite important in barometric calculations, etc. 13,600 kg per meter cube. Okay. Density of wood is generally in the range of about 0.4 to 0.6 gram per cc, something like that. Anyway, so you don't need to memorize all of these. Density of water will be used so often that in questions that you'll end up remembering the value 1 gram per cc, but otherwise data will always be given to you in numerical problems. So density is the first important physical property of any fluid. And in the case of an ideal fluid, it is both uniform at every point and independent of pressure. Needless to say, as you know, density is a scalar quantity. Okay, now the next thing is, the next important property
Please
is, yeah.
So लिखना बाकी.
Okay.
No, sir, done.
Okay, done. Okay. Now the next important property, physical property that we see for any fluid, and in this case we'll be studying about ideal fluid, is the property called pressure. So we say pressure exerted by a fluid. So can anybody tell me what is pressure? How we define pressure?
Force per unit area.
Very good. Force per unit area. Okay. Dhruv, to answer your question, relative density typically does not have any unit, but sometimes any symbol, but sometimes we just write it in short as relative density. So for example, relative density of ice is 0.9, or relative density of, let's say, some metal, some particular metal might be 6.0. So it's 6 times the density of water, like that. Yeah, now coming back to that, so pressure exerted by a fluid is force per unit area. So then can you tell me something, should pressure be a scalar quantity or a vector quantity?
Scalar quantity.
Okay, but then if force is a vector, then how come we are saying that pressure is a scalar? You're correct in saying that it's scalar, but how do you explain this, that you're defining it as force per unit area and force is a vector quantity?
So because pressure acts equally in all directions.
Yes, pressure acts equally in all directions, or in other words, the way pressure acts, it's independent of direction. So the more proper definition is now the direction in which the force will act because of pressure That depends on what? It does not depend on any direction in particular, but it depends on the direction of the surface itself, because the direction of the force is always perpendicular to the surface. Are you
Yes, sir.
understanding my point? No? So for example, if we are measuring pressure by measuring the force per unit area on an imaginary tile, let's say I've taken a square tile, okay, and I want to measure the pressure at any point inside a fluid. So I place this tile inside some fluid, okay, and I want to measure the pressure at some given point in the fluid. So now you'll see that if I place the tile like this, then the surface of the tile which is facing upwards, that will experience a force like this. Okay, this is the direction of the force. And if its area is A, so I'll say, okay, the pressure is equal to F divided by A. But the same tile now, if I was to change the angle at which it is placed, so now I place the tile like this. So the surface I'm talking about is facing in this direction, perpendicular. Okay, and it's inside the fluid. So now the force due to pressure that it will experience,
Surface area comes, so pressure will happen.
it will now automatically, the force's direction will change in such a way that it will become again normal to the surface. So the force's direction is not affected by anything else. It is just affected by where the surface is placed. It's always normal to the surface. Okay. So another better way of expressing it is that the pressure exerted by a fluid equals to the normal force. Normal means perpendicular. Okay. So the direction of the force is always normal to the surface. The normal force per unit area experienced by a surface, okay, due to the fluid. So that then also brings the question that, do I define pressure as, delta F by delta A or dF by dA, etc. So then that brings the difference between the quantity average pressure versus the absolute pressure, or you can say instantaneous pressure at a point. So average pressure will be like the total force upon total area. Okay, that is the net force normal to its surface divided by the surface area. Okay. So this is the average pressure experienced by any surface inside a fluid. So that is the example of the tile that I placed over here, that the total area of the tile is A, and the total force experienced by the net force perpendicular to its surface or normal to its surface is F. So F divided by A becomes the average pressure experienced by the tile. But the instantaneous pressure, that we'll have to define like this, that it is delta F by delta A, with the condition that, like a differential condition, that delta A should be as small as possible. So this is like the instantaneous pressure at a given point. Instantaneous pressure at any given point inside a fluid. Okay, so say this is a container of fluid, and I want to find the pressure at a particular point like this. I want to find the pressure at this point A, okay, or let's say at this point something else, Q. So what I'll have to do is I'll have to place an imaginary surface at that point, which is a very, very small area. So delta A tending to 0. So that imaginary surface will experience a normal force of delta F. So that normal force per unit area for that very small imaginary surface, that becomes the instantaneous pressure at that particular point Q, where I place that very small surface area delta F. And
So
again,
the
the
point
direction of the delta F will be according to the direction in which I place the surface. It will be always normal. Yes, beta. What was the question?
So point mass के equivalent रहेगा.
But see, this is not some actual mass that I've placed over there. No? It is an imaginary surface.
Okay.
You understanding the point? So you can better think of it like this, that if you were practically thinking of this like an experiment, so at a particular point you want to measure the pressure, what you do is you place like a very small sheet of cardboard or like a chit of paper. Okay, so wherever the chit of paper surface is facing, the direction of the force acting on it will be perpendicularly into it. And if that sheet of paper is very small in size, we can write its area as delta A tending to 0. So then the ratio of that delta F by delta A will become the instantaneous pressure at that point where that sheet of paper is present.
Okay.
Is it clear, Viraj?
Yes.
Okay, so this hopefully explains both the points that pressure is a scalar because the direction of the force is already decided. It's actually like the component of force, it's normal force. So component of a vector is a scalar quantity, remember. So the moment we say it is the normal force exerted per unit area, we're talking about a component of a force divided by the area. So it's a scalar quantity. And the second thing, the difference between average pressure and acting on an entire surface of area A versus instantaneous pressure at a particular point on that surface. So that is delta F by delta M. So keep in mind that pressure is a scalar. So now a static fluid has this very interesting property. Now, because of pressure, it applies force on any surface it is in contact with, always in the direction normal to the surface. That's not how, for example, a rigid body behaves. For example, a rigid body will only, generally speaking, apply force when it is in contact with the surface in such a way that there is some normal contact force. So if I have a rigid body like this, and I place it against another rigid body like this, but there's nothing to press them against each other. Okay, and of course, this whole combination is on some horizontal surface like this. Okay, so now we can see that the rigid body, which I've labeled as A, okay, the rigid body A applies pressure on the floor. Okay, and that will be equal to like the normal reaction force divided by the contact area. Okay, but if this body is now B, unless they are pressed together, okay, but A does not apply any pressure, on B because there's no normal reaction. Okay. But unlike that, a fluid is very different. Okay. When we talk about a fluid, so this is a cylindrical container inside which I've placed a fluid. Okay. It need not even be an ideal fluid, it could be any liquid also. Okay. But the moment I've placed any body inside this, now you see something very interesting. Any surface on that body will experience force due to pressure. This wall will experience a force like this. This wall will experience a force like this. This wall will experience some force like this. So that is because the liquid has this property of applying pressure independent of direction. Equal pressure in all directions at a given point. So all surfaces, any and every surface in contact with the fluid experiences normal force, like a normal contact force due to pressure. So that is a property that fluids have. And in general, we can say fluids are all categories. Fluids can be gases, liquids. Okay, liquids includes both ideal and non-ideal, everything. But of course, in this chapter, we will limit our discussion to ideal fluids. Okay. So atmospheric pressure is once again the same thing. Okay, so now we come to one of the most important aspects of this chapter, the variation of pressure inside a fluid. So this section, it is called, before that, what is pressure measured in? Okay, so the unit of pressure is Pascal, the SI unit, that is. Pressure is measured in pascals, so the SI unit. Okay. 1 Pascal equals to 1 Newton per meter square. Okay. CGS unit doesn't have a specific name, but it is dyne per centimeter square. Okay. Now there are some other types of units of pressure also, okay, which are like barometric units of pressure. So I will come to these in more detail when we understand about a physical apparatus called barometer, which, as you know, is used to measure atmospheric pressure. Okay. So we'll discuss about these units later. There is a unit called atmosphere. There's also a unit called bar. There is also a unit called torr. So for example, 1 atmosphere is equal to basically 1 bar, which is equal to about 1.01 into 10 raised power 5 pascals. You've seen this in heat and thermodynamics also. Okay. And sometimes we also express in barometric way, we also express pressure in centimeters of mercury. Pressure can be expressed in centimeters of mercury. Okay. So I'll explain how this works when we discuss about the barometer. Because it's all connected to what we are going to study next, which is about the variation of pressure with position. Most importantly, the variation of pressure with depth. That density into pressure in density into acceleration due to gravity G into H, the height, that formula that you know, that when you go to a height H inside a fluid or to a depth H inside the fluid, the pressure increases by density into G into H. So we'll look at that formula and that whole concept very closely and understand why that happens also. So all the properties of a static fluid, like for example, its property of pressure itself, okay, then the buoyancy property or the upthrust or Archimedes force that it applies on any body when you put it inside a fluid, all these kind of physical properties are as a result of how the pressure varies inside a fluid. So that is the most important section of this chapter, which we are coming to next. Pressure variation. Okay. Inside is static, and we are back to ideal fluids. We are discussing ideal fluids here. So this we study in terms of pressure gradients. Okay. That is rate of change of pressure with respect to position. Like for example, in work energy, you had studied that internal conservative force is negative of gradient of potential energy, or in one dimension it becomes that F is equal to minus du by dx. So this is an example of gradient. Okay, negative of gradient of potential energy is the x component of internal conservative force. That was an example of the application of the concept of gradient. Okay, so as we discussed, that rate of change with respect to position is called gradient, whereas rate of change with respect to time is simply called rate of change. Okay, so we say acceleration is the rate of change of velocity, but we say that internal conservative force is the gradient or negative of the gradient of potential energy. So that term gradient. Okay. So we will use a sort of standard notation here where we will take the y-axis as our vertical axis and the x-axis as our horizontal axis. So having done that, we will understand two types of gradients: horizontal pressure gradient and vertical pressure gradient. Okay. So consider now like this kind of a shaped container which is having some ideal fluid inside it. Okay. It's having ideal fluid up to a certain height inside it. Density of that ideal fluid is rho, and acceleration due to gravity is like this. So this is the vertical dimension. So now, as I said, we will take the vertical axis as a y-axis and the horizontal plane as the xz plane. So y-axis is the vertical, okay, and the xz plane is our horizontal plane. Okay, so del p by del y. Now we'll use that gradient, that partial gradient notation. This is the vertical pressure gradient. And what we expect is that this should be a negative quantity, because as we go up, pressure decreases, or as we go down, pressure increases. So this should be the vertical pressure gradient. Okay. So as we know from everyday life, this is expected to be a negative quantity because pressure decreases as we go up. Whereas del P by del X and del P by del Z, they are both horizontal pressure gradients. So those are horizontal axes. Okay. So generally speaking, again from everyday life experience, we know that these are expected to be zero. Okay. So now we'll just demonstrate why these are zero and why this is negative and exactly how much it is. How it depends on density, how it depends on G, etc. So that is the derivation that we are considering doing next. This is a static fluid sample. Yes, Shikhar, what you're saying is true. Because pressure increases with depth. So any kind of machinery or device or whatever that is built to function underwater, like a submarine is a structure which is meant to function underwater, there is a maximum limit to which it can go because the structural integrity of the submarine is designed to withstand up to a certain amount of pressure. So if it goes beyond that, then the excess pressure beyond the structural integrity limit will cause the structure of the submarine to get damaged. Okay, so I'm just scrolling up for a minute because people have requested. Okay, let's get back to pressure gradient. Okay, so let's understand the calculation of this pressure gradient. So let's imagine that this is like a water tank, okay, which is at rest with respect to the ground frame. So in the Earth's ground frame or an inertial frame, this is at rest. And let's apply fundamental mechanics to this. That is the concept of free body diagram. And let's see how we can show that vertical pressure gradient is going to be negative, and how much the value is, that also we'll see. And horizontal pressure gradient is going to be 0. So this is in an inertial frame. Let's say that is the ground frame, and this is at rest. Okay. So now what we are going to do is to understand the vertical pressure gradient. First, we will imagine that we have taken a section of this one's volume. Okay, so we have taken what we call a volume element of the liquid. So this is not a separate body. This is part of the liquid only. But imagine that we are making the FBD of this small volume element. So this is a volume element of fluid. This is not a separate body of the same fluid that is present over there. And this volume element, when we draw a magnified diagram of it, because it's a small element, this thickness is dy, whereas this area is delta A. Okay, so the volume of that fluid element is equal to its area into its thickness. So the mass of that element, let's say delta M, is equal to density into volume. So rho into delta A into dy. That is the mass of that element. Okay. Now next up, let us look at the free body diagram of that fluid element. Okay, let's look at its FBD. So we are in the inertial ground frame and its acceleration is 0. Okay. But now in this FBD, we'll consider only vertical forces. Considering only the vertical forces. We'll come back to the horizontal forces later, but considering only vertical forces. So what are the vertical forces acting on it? Obviously, there is its weight.
Yes.
Okay.
And
that is, let's say, delta M into G. But what is keeping it from coming down like this? Because there is the load experiencing some force due to pressure. Okay.
yes.
So that force due to pressure, let's say, is delta F, which is equal to pressure into that area. Okay. But the upper surface will also experience a downward force, and let's say that is delta F prime. So that will become P plus delta P into the area delta A. Now what we have to show is that this delta P is a negative quantity, that's the pressure decreases as we go up. So in this equation, what is happening? P is the pressure due to the fluid at, now from the bottom, if we consider this height to be y, okay, at y equal to y. So P plus delta P. Okay. In fact, instead of delta P, we'll write it as dP, because it's a very small change in pressure. Because the change in height is very small, it's dy. Okay. So this is P plus dP into that area. So P plus dP is now the pressure at a different y coordinate, at y equal to y plus dy. Okay. Because this upper surface, its y coordinate, as you can see in this diagram from the floor, its vertical height or its y coordinate we can see is y plus dy, because the thickness itself is dy. So now when we look at equilibrium equation over here, its acceleration is 0. So net force must be 0 vertically. So this delta F prime plus delta mg must balance delta F. The two downward forces must be balanced by the single upward force. That is how that volume element of fluid is remaining at rest the way it is. It's not falling down. So that shows me here next when we substitute that P plus dP into delta A is equal to, plus the weight. So that weight of that section is the mass, which is density into volume. So mass into gravity, okay, acceleration due to gravity, is equal to delta F, which is P into delta A. So next, when we cancel off the delta A and also the P, we get this relation that dP is equal to minus rho G dy. Now this dP is the change in pressure
In vertical direction.
Yes, okay, for a vertical displacement of dy. So we can write dP as the vertical pressure gradient del P by del y into dy. Okay, so we can substitute that over here and we can see that the vertical rate of change of pressure into the vertical change in coordinate, that's the change in pressure, that is equal to minus rho G into dy. So that is telling me that the vertical pressure gradient is as expected a negative quantity, and how much it is equal to minus rho G. So we have a uniform negative vertical pressure gradient. That means pressure decreases with respect to vertical height at a uniform rate. If I were to draw a graph of pressure versus height, it would be a graph of reducing pressure, but a straight line graph because it has a uniform gradient.
Okay, sir.
So this shows me that pressure decreases with vertical coordinate at a uniform rate. Okay. So if we draw a graph of pressure versus the vertical height, so it should be decreasing like this at a uniform rate. It should be a straight line like this, and it should have a slope of minus rho G. And ultimately, this will only give us the formula of rho GH, that if I go down
Sir,
through a height h, yes.
so the partial difference is because it was in a three-dimensional space, that's why.
Partial derivative क्यों लिखना पड़ा मुझे? Because what I'm assuming is that pressure is a three-dimensional function. It is a function of x, y, z.
Sir, actually it's a tensor, right? Tensor ranks.
Yes, it is a tensor actually. It's a rank 3 tensor. Okay.
Yeah.
So del P by del Y is the vertical gradient, and the other two are the horizontal gradients in mutually perpendicular directions.
Yes, sir. Understood.
Okay. So this is a proper vector calculus way of expressing this whole thing, that how the pressure varies with position. Okay, so just to repeat this, what we're doing here is that we're understanding that XYZ coordinate system is such that y-axis is vertical and x and z axis are horizontal. Okay. Now, if the pressure we assume varies with all three coordinates x, y, z, then there should be vertical pressure gradient del p by del y and horizontal gradients del p by del x and del p by del z. So to calculate the vertical pressure gradient, we are making the free body diagram of this volume element as I've shown you. Okay, where this volume element has a vertical thickness of dy and a cross-sectional area of delta A. So we are showing its equilibrium because of the vertical forces, that is the weight and the two forces acting on each surface of that cylinder. Okay, of that thin cylinder of thickness dy, the upper surface is experiencing a downward force which I've written as delta F prime, and the lower surface is experiencing an upward force which I've written as delta F. So these three forces should balance. So on balancing these three forces, we can see that as you go from the y coordinate of y to y plus dy, the change in pressure dp is given by this quantity minus rho g dy. So this equation itself is showing us that the pressure decreases as we go up. And in fact, as we go up by a small displacement dy, the pressure decreases by a factor of minus rho g dy. So now we can say that, okay, that change in pressure dp is nothing but the vertical gradient del p by del y into the vertical displacement dy. So from that, we are now getting that the value of the vertical gradient is minus rho g. That means as you go vertically up inside the static fluid, the pressure decreases at a uniform rate and at a uniform slope of minus rho g. So Yashmit, hope this is clear now.
Yes, sir.
Okay. What happened to people? Okay, so this is about the vertical pressure gradient. Now let's see how we can, in this case, very simply prove that the horizontal pressure gradient is zero. Because now if we take a volume element such that it's like a thin cylinder, but
Placed horizontally.
yeah, its axis is facing horizontally. If we take that kind of cylinder, okay. So the cross-sectional area is in the vertical plane. So if we take a cylinder like this now, where this thickness is, let's say, okay, so we have placed it from here at a distance x. and this thickness is dx. And again, these areas are delta E. So now we want to show the horizontal forces on this volume element. We're not worried about the vertical forces because we've already shown in the previous diagram how the vertical forces are balancing. Okay, so we can see that the horizontal forces. Now, if we assume pressure is different from both the sides, then we should write this force as pressure into delta E, and we should write this force as P plus dP into delta E, where dP is this time pressure variation with respect to x-axis into dx, because P is the pressure at x equal to x, and P plus dP is the pressure at x equal to x plus dx. Okay, so dP is the change in pressure as we are changing the x coordinate by dx. So it is rate of change of pressure partially with respect to x into this. So that relation here. But now we can see that this is with respect to my inertial frame. It is at rest. So the two horizontal forces have to balance. So that is showing me that dP is 0, which is showing me that del P by del X is 0. So there is no horizontal pressure gradient. And likewise, you can see symmetrically that del P by del Z will also be 0. Okay, because you just have to turn that by 90 degrees in the horizontal plane, okay, this area element or this volume element, okay, and make its axis along the Z axis, and you'll be able to show the same. So this is what shows us that there is no horizontal pressure gradient inside this kind of a tank, but there is a vertical gradient which is negative and uniform, equal to minus rho g. So what that means is that if I go from one point to another horizontally, the pressure will not be changing as I'm moving. So if I move in the xz plane, the pressure is uniform at all points, or any plane parallel to the xz plane, any horizontal plane, the pressure is uniform at all points. But the moment I change my vertical coordinate, okay, the pressure is changing. If I'm going up, the pressure is decreasing. If I'm going down, the pressure is increasing, and proportional to the displacement, because the rate of change is uniform. So that's something that we know about fluids from a long time now, but this is just a vector calculus way of showing it.
Sir, can you please explain the free body diagram again?
Okay, so the free body diagram we are considering is for like a very small cylinder of fluid, such that that cylinder's axis is along the x-axis. You understanding this diagram?
Yes, sir.
Okay. So that cylinder's cross-sectional area is delta A and its axis is along the x-axis. And in the free body diagram, we are only considering the horizontal forces. So what are the horizontal forces on this volume element? This drum-like structure, this imaginary drum of liquid, it is bounded by two surfaces. There are two discs on either side. So each one experiences a normal force going into the disc, which is pressure into area. So those are the two forces. And because it's at rest, you don't see that volume element moving inside the fluid. No, it's not accelerating. Its net force should be 0. So the two forces should balance from either side. That basically means that whatever is the pressure at one side should be equal to the pressure at the other side, or dP should be 0.
Yes, sir.
So now what this basically means is that, for example, if we consider this kind of body of liquid or this kind of container having liquid inside it. So if liquid is filled up to this level and it's an open container, so now if I label this point inside the liquid as E, okay, then directly below this another point at a depth of H is B. And then at the same horizontal level of B, I have another point which is C, but which is at a distance at D. So we can see that pressure difference between A and B will be equal to, so we have del P by del Y is equal to minus rho G. So when I'm making a vertical displacement, the change in pressure is del P by del Y into dy for vertical displacement. So as you can see, between A and B, there's a vertical displacement. So I'll have to use the vertical gradient formula. So it means that PA minus PB. So this is minus rho G into dy. So because this is a constant quantity, so now what I can say is that delta P is minus rho G delta Y for a vertical displacement of delta Y. Okay. So this statement now we can directly interpret it as this, that when I make a vertical displacement of delta Y, my pressure changes by how much? Delta P equal to minus rho G into delta Y. So now when I apply it to the points A and B, so I can see that delta P is, let's say, PA minus PB. So that should be equal to minus rho G into the vertical displacement from H from B to A, which will be plus H. So that is why the pressure at the point A is lesser than the pressure at the point B by rho GH. Or if we invert this, we can say that the pressure at the depth below is the pressure at the surface plus rho GH. So this is the formula that all of us are familiar with. Now, since the point A is on the surface, at an open surface, let's assume, so the pressure at the point A is equal to atmospheric pressure. So if we know the depth of any point with respect to the open surface, if the depth is H, then we directly know that the absolute pressure at the point B is equal to atmospheric pressure plus rho GH. So for example, if the density is 1 gram per cc and we're taking G as 10 meters per second square, and suppose the depth is, let's say, suppose the depth is 5 meters, okay, then the pressure at the point B will be 1.01 into 10 raised power 5 pascals, that is atmospheric pressure, plus 10 raised power 3 in SI unit into 10 into 5. So as you can see, this will become 1.51 into 10 raised power 5 pascals. That will become the absolute pressure at the point. Okay. Now, as far as C is concerned, C is the point C, the way I've drawn it, is at the same horizontal plane as B. Okay. So the pressure difference between B and C should be 0 because del P by del X,
Horizontal.
horizontal gradient is 0. Or we can say that C is again at the same depth H with respect to the point A. So the pressure at the point C should be equal to the pressure at the point B, which is P naught plus rho GH. Okay, which in this particular case would become this much. Okay, so of course, when you substitute the density, don't forget to convert it to SI units. So it's 10 raised by 3 kg per meter cube. So basically, I have considered water, okay, and I'm going into a depth of 5 meters underwater. So you can see that the pressure has increased almost by a factor of 50% compared to the surface. There's something
Yes, sir.
approximately equal to a 50% increase in pressure. And that is why deep sea diving is also very dangerous business. Okay, and it needs to be done with proper diving kit or diving suit and with proper slow pressurization for your body to adapt to it. Because if you suddenly go underwater to a big depth, the increase in pressure versus your internal blood pressure, that pressure difference creates problems. And especially if you go from high pressure underwater and suddenly come up back to the surface level, the sudden drop in pressure will cause you to bleed out because your blood pressure would be much higher than the outside atmospheric pressure. So it's a very hazardous business of deep sea diving and requires a lot of training and proper equipment. Okay, now sometimes this can you can have a situation where you're trying to apply this in a slightly tricky situation or a tricky kind of system, but you have to always stick to the basics that if we are talking about a fluid which is at rest in the inertial frame, then always the vertical pressure gradient will be minus rho g. And the horizontal pressure gradients will be 0. Okay, so we have to always stick to this idea. So from an open surface, if we are at a depth of h, then the pressure becomes P naught plus rho g. So for example, next I have something like this. I have taken a tube, okay, and I've bent it into this odd kind of shape. I bent it into this kind of shape. and I have put a seal on this side. So this side is sealed. Okay, and this is an open. And now I start filling some liquid. So the liquid goes inside like this and fills up. And eventually I see that the liquid is in this kind of position, where, let's say, if I am to measure these, this height difference is h1. Okay, then if I am to measure this height difference is h2, and if I am to measure this height difference is h3. So the density of this fluid is, let's say, 1.6 gram per cc. G is equal to 10 meters per second square. Okay, and now I'm labeling these points. This point over here is A. This point over here is B. And this point just where the liquid is in contact with the upper surface, that point is C. Okay, so just below the sealed end, that is C. Okay, so given that atmospheric pressure is equal to, let's say, 10 raised by 5 pascals, approximate value, and H1, H2, and H3 are given to us. We have to find the values of all this. So H1 is, let's say, 4 meters. H3 is, let's say, 2 meters. And H2 is, let us say, 6 meters. So we want to find the absolute pressure at points A, B, and C. So what you have to remember is that when you move horizontally, there is no pressure difference. But when you move vertically down with respect to the open surface, the pressure becomes P0 plus rho g into the depth. Okay, so it doesn't matter that above the point A directly there's no open surface. Okay, but you take any point on this open surface and you compare that point with the point A. Now, what is the vertical depth? It is H1 plus H2. And the horizontal difference, it doesn't matter because there's no horizontal pressure gradient. So we'll be understanding this point. So use this to calculate the values of these pressures.
One second.
Okay, so I have got some answers and some of the answers are correct. Okay, so let me just verify. So what we'll have to understand is that the reference point for me will be the point on the surface. So let's just say for argument's sake that point is D. So D is the point which is on the open surface. So D is on the open surface. So it is at atmospheric pressure. The pressure at the point D is the atmospheric pressure, which we know is that much, 10 raised power 5 pascals. Okay. Now compare, for example, A and D. You can see that the vertical displacement, that is the y coordinate of D minus the y coordinate of A, is actually plus of H1 plus H2. That means D is at a depth of how much? A is at a depth of how much? A is at a depth of 10 meters. Okay, so this means that A is 10 meters vertically below. So it doesn't matter that it's not directly vertically below. Okay, but if this is the point D and this is the point A, it doesn't matter that it's not exactly below like this. Okay, the displacement between these 2 points is S, but उसका जो vertical component है वो कितना है, वो ये delta y है, और horizontal component कितना है, it does not matter. Okay, so this is this much. So this is 10 meters vertically below D. So pressure at the point A will become atmospheric pressure plus rho g into this H1 plus H2, which in this case will become 10 raised power 5 plus 1.6 into 10 raised power 3 density into g into 10. So that's becoming how much now? This is becoming 2.6 into 10 raised power 5, right?
Yes.
So that is the pressure at the point A in pascals. Now similarly, if you compare the point B, you will see it is at a depth of only H1 plus H3. The point B is at a depth of H1 plus H3 with respect to D. So H1 plus H3 is 6 meters. We just have to replace this depth with 6 meters. Okay. Just a second, I'll reshare the document. So similarly, B is at a depth of H1 plus H3 equal to 6 meters below B. So that makes the pressure at the point D equal to how much? This is just
1.96 into 10 power 5.
At C, no, sir. At
this
B,
is
no.
sorry, this is at B. My mistake. Yeah, this is the pressure at the point B. So pressure at the point B is becoming how much now?
Sir, 1.96 into 10 to the
1.
power 5.
Right. Very good. 1.96 into 10 raised by 5 pascals. Okay. This should also be B below. Okay. And likewise, the pressure at the point C, you can see, is going to be atmospheric pressure plus rho G into C was directly at a height of H1 below, so that's 4 meters. So this is 1.64.
1.64.
Correct, into 10 raised by 5 pascals. Very good. Okay. So this is how we find in any situation, whatever the shape of the container, it doesn't matter. If we have a point which is on an open surface, that becomes our reference point. So with respect to that reference point, we have to find this out. Okay, so hope this is clear to all of you. Now, the next thing is that we have two different terms related to pressure: absolute pressure, okay, and what is called hydrostatic pressure. So hydrostatic pressure is like the excess pressure because of the hydrostatic column. Okay. So you should understand the difference between the two. So if the pressure at a point is equal to atmospheric pressure plus rho gh, because that point is at a depth of h from an open surface. Okay. Then we say that the absolute pressure is P, is the absolute value of pressure. is the actual amount of force per unit area acting on a surface. So this is the absolute pressure at the given point. Whereas we say delta P, which is rho GH, this is what we call the hydrostatic pressure. It is the excess pressure that is there. So if the fluid had not been there, the pressure at that particular point would have been the normal atmospheric pressure. But the presence of the fluid creates an excess value of pressure of rho GH. So this is the hydrostatic pressure, or you can say the excess pressure due to the hydrostatic column above. So that is the difference between absolute pressure's definition and hydrostatic pressure's definition. Sometimes hydrostatic pressure is also called gauge pressure. When you use a pressure gauge, it is generally it's generally calibrated in such a way that it shows 0 for atmospheric pressure. So the value of pressure it shows is the excess above atmospheric pressure. So that's why we also call the hydrostatic pressure sometimes as a gauge pressure. Okay, now let's look at an example of net force on a surface due to the hydrostatic pressure. Okay. So this is one of the direct applications of the derivation of hydrostatic pressure that we've just done. So let's imagine again that we have a container. Now this time let's imagine we have a cubical container, perfectly cubical, of dimension L by L by L, and it's an open container which has fluid filled up right up to the top. So it's an open container with a fluid of density, ideal fluid of density rho filled to the top. So we now want to find the net force acting on both the floor as well as any of the side walls. So we want to find the magnitude of net force due to hydrostatic pressure on the floor and any one of the side walls. Okay. So in the case of the floor, you'll realize it's very easy. The pressure is uniform at every point. So we can directly calculate the pressure as uniform. We can directly calculate the net force as uniform area. Okay. But when it comes to the side wall, the pressure is varying. It's varying with depth. So we cannot directly calculate pressure into area. We have to use integration. We have to take a small area dA, okay, where the instantaneous pressure is P, and calculate the force on that small area as P into dA. And then we have to integrate for all such small areas to calculate the net force on the wall. Okay, so this is one of the standard derivations in this chapter. So let's go through this. Try this out yourself first. No, Shikhar, on the bottom surface, the pressure is uniform, but that's not the same for the side walls. Okay, so that is the idea. So, for example, if I'm taking this square as ABCD, so on that surface ABCD, you can see that at any point on that surface, the pressure is uniform. So at any point on the surface, the pressure, in fact, the hydrostatic pressure, is equal to rho GL because it's at a depth of L.
Yes, sir. Rho GL, right.
So if I take a small area dA, it's experiencing a differential force of P into dA, which is rho GL into dA. So now if I want to calculate the net force, I don't really need to do integration because this rho GL is constant.
Yes,
It's just, it's just equal to rho GL into that area, which is L square. So interestingly, you can also see it is equal to the weight of the liquid. You can see this is nothing but mg, where m is density into volume. This is the total weight of the liquid. Okay, so that's fine. So if you also think of the fluid body, if you think of its free body diagram, then its weight is getting balanced by a sort of normal reaction force. Okay, and this normal reaction force, which is equal to mg, this is only equal to that net force, because that and this are action reaction pair. So the fluid is applying a downward net force on that surface, and the surface is applying an equal and opposite normal reaction upwards on it, which is balancing the fluid's weight.
sir.
Right? Yes.
Sir, we took that DF. F net is different or DF is the same?
Sorry, F net is the net force.
F net, okay. F net into DF you have written or no? That's
No,
the
it is
same.
integration. F net is equal to integration of DF.
Okay.
Comes from summation of DF. Okay. I forgot the equal to sign. It's in between, right? So this is the simple part, the first part, right? Now the second part is where we have to look at the application of integration, because now let's go back to the earlier diagram. Let's understand. Now suppose I take this side wall BC and label these points D and E. So now I'm considering this wall, how force is acting. So I know that the force that the liquid inside will be applying will be some vector like this. This will be the direction of the forces that are acting at various points. So how much is the net force on that I have to understand. So for the net force, okay, so if this is my wall BCD, and of course the fluid is present on this side. So I know that at any point which is at a depth of y, the hydrostatic pressure at a depth of y is rho gy. Okay. So it's varying with y. So if what kind of what kind of volume element I should take? I should take a horizontal strip. I should take a thin strip of thickness dy. So as long as the thickness is less, I can say that the pressure at every point on the strip is more or less uniform. So this thin strip now, which is of thickness dy and length L, this will be experiencing a force due to the pressure of the liquid inside, and that force will be dF. So that force will be the volume, the hydrostatic pressure into the area of that strip. So this thin strip has an area dA, of length into thickness. So further, the force on that element becomes rho gy into L dy. This is this force on that element. Okay. So if you also look at the side profile of the wall, so let's say we are we will see that the different elements, they experience increasing force as you go down because
Yes,
the pressure is increasing. So in fact, the force profile will be like a linear profile because it's varying linearly with y. Okay. So the net force that this experiences is going to be the vector sum of these df's. So which will again come from integration. So it's a very simple integration. So that net force, when we do integration of df this time, rho g into L is constant outside, y dy. Now remember, y we are taking as the depth from the top. So it is going from 0 at the topmost point to L at the lowest point. So this is going to become y square by 2 and put the limits 0 to L. Just a second, people. हेलो, हाँ सत्यजीत, मैं लेक्चर में हूँ ना, बार बार मत कॉल करिए, मैं जब हो जाएगा तो मैं कॉल बैक करता हूँ. Rho g L cube by 2. So this becomes the net force. So you can see that the net force on the side wall is significantly less. It's 50% of the net force on the bottom. And also see, as far as the entire container is concerned, the total force horizontally acting will be 0 because in pairs these will cancel. This surface will be experiencing a force of rho g L cube by 2. So this other face on that side will be experiencing an equal amount of force. In this face in this direction, this face in this direction. So the net horizontal force will be 0. Okay, so on the whole, the net force that the liquid is applying on the container is the vector sum of these three forces that I've shown, or rather these four forces, and the force acting on the bottom of the container, which is in this direction. And that force was different. That was rho g L cube. So these four will cancel in pairs, and what will remain is just this. So overall, the liquid is applying a net force on its container of how much? Only rho g L cube downwards. But each of the walls is experiencing a sideways force, which is equal to half its weight.
yes. So it will be 4 times of and 2 times.
Sorry, it will be?
So it will be 4 times of the F net of the side one.
No, vector sum beta 0 ho jayega na. You understanding?
Opposite direction में तो cancel होगा.
Okay, so the net force on all four side walls together is going to be 0.
Okay.
So
Sir,
the
but
net
on one side it will be rho g L cube by 2 on one side of the container.
Yes. This is the magnitude of the net force on each side. Okay, so this is one of the important and interesting aspects of the application of pressure gradient. Now the next property of the fluid we'll see is something called Pascal's law. You might be familiar with the principle of Pascal's law. For example, if you've seen a hydraulic lift or a hydraulic elevator or any kind of hydraulic based machinery, okay, hydraulic presses, etc., it works on the principle of Pascal's law. So the statement of Pascal's law is this, that any change in pressure, okay, created at a point in a fluid is transmitted uniformly to all other points. In it. Okay. Of course, we are dealing with an ideal fluid. Okay. So a simple way to understand would be that suppose I were to do something like this, that I have a closed container, okay, in which I have kept some fluid up to a certain height. And suppose what is happening is this part initially has air at atmospheric pressure. Okay, this is a closed sealed container. So there's some air over here and there's a fluid of density rho. So now if I see a point like this over here and compare it with another point B below at a depth of H, so I can see that the pressure at the point A is equal to atmospheric pressure and the pressure at the point B is equal to P naught plus rho GH. Okay. Now next what I do is in the same system, I create a change by using a pump. Okay. So either I can pump in air or I can pump out air, whichever I want to do. So let's say in this case, I have chosen to pump out some air. So I've used a vacuum pump to pump out some of the air. I've not vacuumized it completely. Okay. So I've pumped out some of the air, and now the remaining air that is here, that is at a new pressure at P naught minus delta P. So what will happen is that this point on the surface, its pressure will now change to, let's say, PA prime, which will be the air pressure outside. Okay. So the pressure at the point B will now change to this. Okay. So when you substitute, you can see that the pressure at the point B is also changed from P naught minus rho GH to P naught minus rho GH plus delta P. So you can now, if you compare these values, you can see that the change in pressure for the point A, which is the final value minus the initial value, was minus delta P. Okay. The change in pressure for any other point B in the fluid also is the same. So any pressure change that I've created at a point on the fluid is equally transmitted to all other points inside the fluid. So this is an example of how that works in case of Pascal's law. Similarly, if I pumped in air and increased the pressure to P naught plus delta P, then both these points A and B, their individual pressures would have increased by the same factor of delta P. So that is what we mean by saying that the change in pressure is transmitted equally to all points or uniformly to all points. So just make a note of the statement and this example. Then I'll also show you how this is used in building hydraulic based lifts or hydraulic based equipment. Hydraulics has applications in heavy machinery, in robotics, etc. also. In fact, it's quite a significant part of mechanical engineering, the working principle of hydraulics and the design and structure and Okay, so let's see the working principle of hydraulic lift. So basic example of a hydraulic lift is something like this. We have, let's say, two parallel columns of liquid. Like this. This is like a tank which is joined together like this. But also, now each side has a piston. This piston is floating on some high density liquid. So this piston has area E1 and this piston has area E2. Now, for example, we can balance a very heavy weight here by applying a comparatively small amount of force here, because the change in pressure is equally transmitted to all points. So if this point is A and this point is B, so the pressure at the point A should be equal to the pressure at the point B. Now the pressure at the point A, assuming that these are light pistons, okay, so the pressure at the point A will be atmospheric pressure plus the weight of that object divided by that area A1. So that should be equal to the pressure from this side, which is P0 plus F upon A2. So comparing, you can see that F by A2 is equal to mg by A1. So F, the amount of force we have to apply to balance the weight of that object, is only a fraction of the weight, because A2 is a fraction of A1. So for example, if A1 is equal to n times A2, where n is obviously greater than 1, then the amount of force we require to balance the weight is only mg by n. Okay, and by pushing piston A2 down slowly, okay, the weight mg on the other side is pushed up. So using a much lesser amount of force, we can push up a much larger amount of weight. Okay. Or sometimes we can design this hydraulic system in such a way that we don't even have to apply the force vertically downwards. We can push a piston horizontally, and on the other side, a large load will be lifted up vertically. This is an example of the hydraulic lift. Another example of a hydraulic system could be like this. So one piston is here of area A1, and one piston is like this of area A2, and this section is filled with fluid. So when we apply some force F2 on this side, it generates a force F1 on its own here. So F2 upon A2 is equal to F1 upon A1. So you can not only multiply the force by a factor, you can also change the direction in which the force is acting, the axis along which the. So this is also an example of a hydraulic system of transmitting force. So you can imagine this is a very important part of heavy machinery in mechanical engineering. Okay, so with that, we complete today's session, people. Based on this, you can work out some questions from H.C. Verma. So hydrostatics or fluid mechanics is again in H.C. Verma part 1. Plus hydrodynamics, actually. They are both in one combined chapter called fluid mechanics. So based on today's concepts, you can do questions 1 to 8 in that fluid mechanics chapter from H.C. Verma. And you can also start from your module, the in-chapter exercise, etc. Okay, so that's it for today's session, people. Wish you all the best. Thanks for attending.
Bye, sir. Thank you, sir.
Thank you, sir.